Okay, thank you to be here for the lecture of today. Let me repeat very shortly just the simulations of last time, because you remember at the end was a little bit too fast. And yeah, you remember I told you I don't remember why some values of the parameter q, and it probably wasn't a question for students, and then I forgot to reconsider the original values. In fact, you remember we were not able to see how sensible the Kalman filter with respect to the parameter q. The reason is that we had a saturation in terms of k. I will clarify what I intend. Let me reconsider now the file of last time. We have here the value of the motor. We will see when I will consider the model of the bank, the model of the bank, that is not far away from this. The model of the bank is not far away because, at least in the model which I would like to present here, in the linear case, which will become a nonlinear case in terms of extension. We will see today what is the meaning of extension, which came from augmentation. Look, here's the data with the matrices, with the discretization of the matrices, run. And then I will open now the Kalman motor, which is the M file, which is connected with the Simulink file. Do you remember last time I told you here it was in very large value? And remember, I had some doubts why this large value. Probably at the end of the student asked me to go more in depth about the meaning of this Q. You remember, Q represent the uncertainties of the model. The name is model noise. What I don't know about the model. Of course, it's a quite abstract parameter. Roughly speaking, do you remember when we discussed the model with the system with just one variable? This was a little bit easier because do you remember I told you if the model is in a constant, if I know exactly that I am trying to estimate in a constant, the model of the constant, the uncertainties of the model of the constant is just its discretization. Because to discretize something is not exactly what I want to discretize. We have an error in the discretization. In the sense, the model is extremely easy. But you remember in this example, I tried to estimate a sine function. The sine function is not constant. This means the model of my a priori knowledge is totally wrong. And you remember, I play with the Q in order to estimate, nevertheless, the sine. I don't know if you remember. When I was young, also now, I am always also now surprised of this concept of which is the base knowledge of the Kalman filter, or better to say, it's a statistical concept. I mean, we say to the Kalman filter that I don't know if my a priori knowledge are correct or no. And inside this variance, because if you have a variable, we don't speak about covariance, like here. Covariance means that we have interaction between two variables. Nevertheless, typically we give just uncertainties in terms of variance. You remember the diagonal and the variance, because the covariance, at least in terms of Q, is really difficult to be interpreted. But anyway, this is the uncertainty of the model current. This is the uncertainty of the model velocity. Now, if both uncertainty is very large, if you remember a little bit, the parameter k, the Kalman k, is somehow proportional to Q, but somehow inverse proportional to Q. I show you now what I want to intend. This means this is very large. We have a Q that cannot change. This means it's not sensible if I change the value of Q. At least I have to reduce in order to have a difference between the cases. I show you what I intend. Let me open now the Simulink, if I am able to find the Simulink is here. I am opening the file. Okay, let me share. Let me show what we have seen last time. It could be that I changed the remember, but now I will be able to show you a little bit the differences. I hope. I have to define the global variable. Excuse me, I forgot. Oh, I defined. I don't remember. It could be that this I find. You see? Let me see. I don't think so. That is correct. Let me look what happens. Let me see. Yeah. Yeah, this is a little bit the results which we have with this parameterization. Now, look what happens. What happens if I want, for instance, to I don't know if it is possible. Let me see. Why I'm saying if it is possible. It depends if I can change using Q and R the variable K, the Kalman gain. The reason is if you look at the equation of the Kalman gain, let me show you again the presentation, the basic presentation. Let me see here in order to clarify what I intend. Okay, let me show you. I intend to say this equation. In order to improve the correction or to change the correction, I have to be able to demonstrate to maintain the variation of KK. No, at least this is when let me see important component, no? Because we have the model which cannot be directly changed, or at least not using KK directly, but KK import more or less the innovation. What is KK? We can see here. We can see that KK depends on P minus in the numerator, let me say multiply by something p minus, this here, up to -1. But p minus, if you remember, depend directly, or let me say linearly, on q. Let me show you. It could be nice if I go to here, better. Again, this is the final, let me say, or the last step of the Kalman filter, let me say, or the correction step, better to say, at each step to be more precise, in which kk influences directly the correction. Now, kk, if you look here, depends of p minus and p minus half to -1, basically. But p minus half to -1, as I told you, depends linearly of kq. This means if q is too large, we have a saturation of kk. Think about, roughly speaking, this is very large, divided something very large, both linearly depending. This means for very large Q, have to be careful because it could be that the Kalman filter does not react. This is the reason. This reflects nevertheless that the component of let me say the deterministic component, the component of the model should not be so let me say full or so full of uncertainties. Better to say the uncertainty of the deterministic part should be so high. This is the let me say in a possible interpretation of this sentence here. This says that the most important part, or in order to work properly, we will come back on this concept later, the deterministic part is extremely important in the Kalman filter. In fact, if you consider just we will see this, the stochastic part of the Kalman filter, or if you increase too much the stochastic components, we end up in some unobservable situation. About the observability that I told you. Now, coming back to the practical application. Yeah, this means if I reduce this, for instance, I don't know now, also with respect to R, if it's more or less sensible, because R is also in the denominator, let me say denominator, in this case, it's not the denominator, but is the component up to -1 of K. But of course, when this is very small, it could be that K is not so extremely sensible. The reason is we can see from here. If this part here, the variation of R with respect to, in this case of P, is very small, is not sensible. Also, in this sense, we can say that KK is not so sensible. We say that is the saturated also with respect to R. But let me show. It could be that it's not. And then we will try to discuss what happens. Let me run. A little bit better? Yeah, it seems. Better or worse is I'm not sure. I didn't check. Let me show you. Let me discuss probably. Keep in mind this should be nice if I put the measurements of the error. I can do that. But look at this, for instance. Just observe what we have. Let me say that we have a good approximation or estimation starting from 0,03, right? More or less 0,03. Now, let me show you and change it. If I increase this, I increase consistently. This means somehow I am decreasing, if it's not in a saturation, the component or the parameter K, or let me say the components. Okay, we have two components of K. We have two states and one measurement. K basically is a column with two components. But in so doing, I am reducing the component of K. This means I am trusting more the model, because I will import less measurement. Let me show you what happens. Oh, the measurements contribution. Seems to be not very sensible, but let me show. I cannot say much on this. Let me do another example. Let me reduce this, for instance. If I reduce this means I am trusting more the model of the velocity. This means, let me show you. Trusting less the measurements. Now we see that the big differences, we will try to interpret it. Let me show you. The reason is, now it's clear what I intend. The reason is, it's clear that we are trusting more the model, particularly the variable omega, better to say the dynamics of the variable model omega, the velocity. And of course, the correction part is less important. And we will see that we don't have a strong corrections. And it could be that we remain with the bias, or the bias is correctly very slowly. Let me simulate a little bit longer. Conclusion. Considering the parameter Q and R, and not only P0, I will repeat a little bit about P0, we can really change the performances or the performance of the Kalman filter. Nevertheless, we can see that the Kalman filter reacts, and very slowly, we can see now, slowly as before, it seems, because before was 0.03. Now we are definitively slowly, but it gets nevertheless the results. But it needs time, because it needs time to understand that we gave not correct information in the sense. Do you remember I told you also last time a similar consideration, considering P0, the error, the initial error. I show you what we can do with the initial error if we don't have also saturation. We can see now that the Kalman filter slowly understands that the what we did at the beginning, the information at the beginning on the let me say the a priori information, extremely important. No? The a priori information is extremely important for the Kalman filter house in different phenomena, also in our life. What we have what we know in advance, we can see that nevertheless slowly the Kalman filter will converge. Let me conclude this short repetition considering P0, because P0 is related to the question which I received. Let me show you P0, what I intend. Let me share, let me stop. Let me share here. P0 is the initial error or the covariance error. But we gave, as I told you, just value related to the variance. Typically, it's so because to interpret the anti-diagonal elements is extremely difficult. This meaning of this and this here is really difficult to be interpreted. But here is the variance, the initial variance in terms of current and in terms of, but of course, in terms of current and in terms of velocity. This means looking at the velocity, let me see if I am able to improve the initial error, increasing the initial error improving means to estimate better at the beginning. Increasing P0, I am saying to Kalman filter, please pay attention, we are far away already from the beginning with respect to the goal. Let me show you, if we are not in a situation of saturation of K, starting directly from the beginning, should be possible to minimize this difference. Now we have a difference also at the beginning. I don't know, depends if it's saturated or not. 1,400. Let me see. Yeah, it's interesting that we have a phenomenon the peaking phenomenon, because we can see that at the beginning the Kalman filter react negative. We can see this is an important effect that it could happen because Kalman filter, let me say, cannot distinguish if the error is positive or negative. This means this is the question which I receive, it's not a question which I receive, but very often I receive this question. The reason is that the error which we put is the variance. This means it's an error square. I don't know if you remember in statistics. The variance is something square. This means could be negative, could be positive. This is a problem which we have always in very often in also other forms of estimator, but in particular in Kalman filter, because we give information on the error square. This means could be positive, could be negative. This means to increase this, we could have also this kind of effect. We have to be careful. Let me nevertheless change something before concluding. Let me reduce a little bit. And let me put a little bit this close to the goal. This means we simplify the life of the Kalman filter. I put here not 0, but something different for 0. Here, reduce a little bit. In order to give the Kalman filter the indication that the omega is positive. Yeah. In fact, now we can see, I don't know if we increase, we improve, but in any case, it seems to be corrected, oriented. The value is not increased, we can see, but at least it's corrected, oriented. Let me increase it now a little bit the value of the error. The reason is why it's corrected oriented, because I put an initial value of omega positive. Now, before was 0, putting positive, the Kalman filter intense that's the, let me say, the right direction is the positive direction at the beginning. Let me do two changes. I would like to put here not this one. No, it's correct. This is correct. Excuse me. Increase in here. Let me increase here. I increase the error. This means I am saying to the Kalman filter, please pay attention that we are really far away from the goal. Again, we have this peaking effect. This means increasing the error. It seems to be that I need also to increase the positiveness of the initial value of x. This could be, let me say, some possible problem connected with the initial value of the error. But please pay attention. We are in some critical conditions, because if you look at the value, you have a value that's also numerically can generate some problems. Let me do another changes in the value of variance of the now I lost the orientation where I am, probably here. Yeah. Let me start with this. Again, we have a similar situation, which is the Kalman filter intends at the beginning, yeah, to go in the wrong direction. But the problem is really, I think, that the value which I show you, I think it generate some numerical problems. Let me do the last attempt, introducing a more reasonable values. See? Not yet. Probably have to reduce a little bit. Let me see. Because also the numerical aspects, we will see a little bit later some issue in terms of numerical aspects. These numerical aspects are nevertheless important. This is the best result which I obtained with some more reasonable values. Yeah, it seems to be that now the peak which we have here is the best which I obtained. Yeah, and then the Kalman filter try to estimate the real value. Not the real value is the yellow, which we want to obtain. Of course, if I will start some value close to the goal, should be easy to get the result. Is in the sense I will obtain the result quickly. Yeah, at the end of this idea is that the idea is that what we can say that Q, R, and P0 should be considered as parameter to tune the Kalman filter, because it's not possible to know exactly a priori the value. The question which I received a little bit to clarify again this scheme here, in which you remember I told you that is exactly the a posteriori covariance matrix, or if you like, variance in the case of one variable. And again, if the problem is convex, the convex means linear system of the model, linear model, Gaussian noise is independent, no? R and Q with mean value 0 and known covariance, white, again, noise. We have the possibility to figure out that we have the possibility to obtain the minimum, which could be the minimum in blue, could be the minimum here I did indicate in the red. This region here is the possible, we can see between the two dashed line, we have the region with the possible, let me say, convex P, which we have. Of course, why we have these uncertainties? Because X, which is the X of Kalman filter, the true of Kalman, is defined as a true inside some uncertainties, which depends on Q and R. And the initial value is exactly related to P0. This means everything depends on Q, R, initial value of X hat, which, do you remember I told you also the orientation of the Kalman filter depends on this, and depends on P0. Depends on P0. This is also important because it could be a mismatch between this value here and the P0, because I don't know this one, because inside this region, I don't know if you have the blue line or if you have the red line or whatever curve inside this dashed. This means, of course, I will get the minimum. I will get the minimum. But of course, it could be that any time. We have seen this. It could be that any time. The minimum, nevertheless, is the best estimation, but with respect to the Kalman approach. This means to respect to the Kalman hypothesis. Again, linear model, white, Gaussian, R and Q, Gaussian, independent, mean value 0, with known covariance or variance elements. This does not mean that we really estimate perfectly the reality, because the reality could not respect the hypothesis of Kalman, the hypothesis which I told you now. In particular, we will see today now, the real case could be also not convex. The P of X minus X hat, in this case, I would like to speak about X star, if you want, or if tilde, which is the real, could be also something like that, because the hypothesis of Kalman is nevertheless an hypothesis, an abstraction of the reality. Of course, closer and closer the hypothesis of the reality, we can estimate better and better. What is the meaning of better and better? We can see here a little bit. We can see here that it could be that I will not get exactly the minimum. This means I will have a bias. I will have a larger, let me say, estimation. I mean, look here. If this is the real situation, this is the best approximation. Assuming that I will get it here, excuse me, I will get this value. If this is the real situation, I will show you today. Now, this is the minimal variance. If I get this, for instance, with my algorithm, I will have a larger covariance and bias with respect to to the real value. This could always happen because the reality is not necessarily Kalman reality. We will see now what I intend when this model is not linear. When I have to describe the reality with non-linear model. Now, I hope I will open I hope that I answered the question. The question was to go more in depth on this. Let me open the lecture of today in which I introduce the nonlinear cases, which is not exactly the hypothesis of Kalman. Kalman means, or at least the first or the basic concept of Kalman is the linearity of the model. Model means the representation of the system. Okay, let me open the lecture of today in a short lecture. Then we will see an example. I will introduce with an example using an artificial nonlinearity, which is introduced using an augmentation. But let me at the beginning tell you about the nonlinear discrete Kalman filter. Again, the idea is always the same. Discrete Kalman filter. Again, I don't want to go in depth on the theoretical aspects. The hypothesis, the motivation is always the same. And we can see this slide is exactly the slide which I presented when I introduced the Kalman filter with the same question. What can a Kalman filter do? In a linear case, you have to think that not always a linear model is appropriate to describe the reality. About the linearity, I told you not in detail, I didn't consider the mathematical definition, but you remember I told you in the mathematical model, we have the states which appear linearly. This means having a linear combination. I don't know if you remember math. This means I have the model which appeared I have the model in which the states appeared without multiplication between state and input, without square, without up to 2. This means just something like a constant multiply the current plus another constant multiply the velocity. Then we have the contribution of the inputs. Do you remember at the end, more formally, I told you that I can separate the contribution of the state with respect to the contribution of the input. Do you remember x derivative equal a multiply x plus b multiply u? Do you remember this? Is also in the output equation. No? Probably I have it here. No, I don't have it here. But if you remember what I told you, x dot equal a multiply x plus b multiply u, and y, the output, y equals c or the h multiply x plus eventually d multiply u. We can see that I separated the contribution of x and the contribution of u, but in particular x and u appear linear. This means no square, not up to 2, not particular function, just a linear function or linear functions. Look at this now. The nonlinear case is basically a linearization of the nonlinear model. I will tell you in 1 second what I intend. But it's a linearization non in terms of the prediction. We can see here. Do you remember this expression here? F. If you want, I open the slide. In the lecture number 1. I close. It's a shame. I have to reopen. I put formally this expression. Let me show you. Now where is? Yeah. No, here's the observer. Let me show you what I intend. So we clarify it again. I will repeat again the concept linear and nonlinear. It doesn't work. Really, sometimes I don't understand Zoom. Do you remember? I know it's not here. It's in the original, really in the first lecture. Let me come back. I think it's here. Now, you remember this slide? Ah, yeah, this here. Here, in this, when I introduced this slide, I tried to explain again the concept of linear and nonlinear. The linear case, I repeat it also now, today, the separation between input and state contribution, not only. The state contributions are linear. Do you remember A is in a matrix? This means row multiply column, the X is in a column. We have a combination linear. This means a constant multiply the current plus another constant multiply the velocity and so on. Here, in general, this means in nonlinear case, we cannot have this kind of structure. This means we have an interaction between X and U, for instance, multiplications, whatever you want. But in general, function between X and U, but also whatever kind of function for X, whatever kind of function of U. This means I cannot write in this form here. This F characterized now, we will see the nonlinear case. As I told you, the nonlinear Kalman filter, or the better to say, the extended Kalman filter, which is just in a form of, now where is the lecture? I don't understand really the Zoom. 1 second, I need time to understand. Oh, okay, now. In case we need, please pay attention to what I say. In case we need a nonlinear model, we have many approaches with the Kalman filter. What I can do in this course is the extended Kalman filter, which is the most important. But we have also basically, I would like to say the classical approach again with white, Gaussian, mean value, and so on. As I told you, we have two main approaches: extended Kalman filter is unscented Kalman filter. I have time just to tell you about an extended Kalman filter. The unscented is just an extension, more detailed linearization, or linearization more than 1 point. But let me go ahead with the extended version, which is the most important, the most applied. We find the literature that the extended Kalman filter is a linearization version of the Kalman filter, but it's not a linearization of the model, or better to say, not the prediction, but it's a linearization of the Jacobian, or better to say, the linearization of equation B. An linearization using, excuse me, the words, using the Jacobian in the equation B. Not only, but let me explain this case at the beginning. You can see that I am considering in the linear model here in this expression here we have a nonlinear model in input, and eventually a nonlinear model in output. About the nonlinear model in output, I will tell you later in the next lectures. Here we have at the beginning a nonlinear model in the dynamics, not in the output. Could be also in the output, nevertheless. We can see an H function and a general function. You remember the output in the linear case was z or the y, do you remember, equals c multiply x plus d multiply u. Here is the general function. Now, inside the Kalman filter, the difference between this information and this information is exactly that I am trying to put this model inside the recursive form of the Kalman filter. We can see here, I introduced the approximation, or better to say hat, means, yeah, the approximation, the estimation, better to say, once a priori with minus, which is a function, a nonlinear function of x hat time k minus 1 is again as before the corrected state or the state vector at the step before. The difference between minus and not minus, I already told you, remain the same in nonlinear case. uk minus 1 in case the approximation I didn't write here, but it's exactly what I told you before, in case I'm using a forward Euler or similar, let me say similar approximation without going depth on this. But do you remember I told you backward Euler, for instance, over here k is not k minus 1, without considering any uncertainties. I put here 0. Similar consideration can be done here, but let me go ahead without thinking about at the beginning. Now we will see later. Nonlinear structure in the output. It could be nonlinear output, nonlinear model also in the output. But let me go ahead slowly. In any case, as before, I don't know if you remember, zk hat minus is a function in this sense not of x k minus 1 hat, but is exactly a function of what we have here. If you want, I can come back on the linear case. Let me see if I find. In order to, let me share. In order to, I don't have it. The output is not represented in, but is reflect exactly this here. Also in linear case. There is now, if you think, there is here. Okay, this is the equation A. As I told you before, basically I am considering the nonlinear case or the nonlinear model without any changes. The main change is here. In fact, formally it seems to be the same equation, but A is not the matrix because we don't have here the matrix. In this case, in order to calculate the a priori error covariance matrix, I am using the Jacobian of the system F, or the field F. What is the Jacobian? We can see here. I don't know if you remember in math. The Jacobian is the matrix of the partial derivative. This means, roughly speaking, is as if I approximate around, we can see here, the corrected vector of the previous state, my field or my system, if you like. Of course, consider eventually also the dependence of U of k minus 1 if the matrix here depends on U of k minus 1. But I don't know if you remember Taylor in high school. Here's a little bit an extension of Taylor because we have a field. Field means an F which depends not only on a variable but depends on two variables. This means in this case we have to consider not only the unique derivative, we have to consider the all possible combination of all derivatives. We will see in an example also today in which we have the matrix 3 times 3 to be analyzed in the example which I will present. The rest of the equation is quite similar. I mean, this equation is exactly the same, but look, in which H is basically the nonlinear, if nonlinear, if this is nonlinear. This is a little bit the point. If this is nonlinear, must be considered what I have. The unique difference between D and E formally are the same. This means we don't have to learn much. But H capitalized is the Jacobian, in case the nonlinearity is also present in H not capitalized in the output. And the rest is exactly the same. I mean, today we will not analyze the nonlinearity in H. This means H is exactly as in the linear case. But if H presents or it has some nonlinearity, of course, this H capitalized, it's Jacobian matrix. It's easier to do some exercise instead of clarify with words. Nevertheless, let me show you to understand a little bit better this slide here. Let me see if I have something to show you, otherwise I will calculate for you. I will explain this slide here, which can help to understand the nonlinear case. Let me see if I have here something. Otherwise, I will build. What you see here is basically what I told you before. In particular, we can see here how our approach is basically a linearization of our estimation around the x hat k minus 1. I will show you. I didn't find, this means I found just a recap of Taylor, which can help you in any case. Let me show you, allow me to show you this slide. Look, do you remember in high school? 1 second. When we have a function y equals f of x. Do you remember this expression here? This expression here is the Taylor approximation of this nonlinear function f of x circa, and the linear, in a linear approximation around the point x0. I don't know if you remember, f of x is circa f at point x0 plus the derivative of x of f calculated at point x0 multiply x minus x0 plus everything that is going to 0 faster than linear. If you to be precise, if I write this, I have to write circa. This I added later. Forget this. I mean, f of x in linear approximation is circa this. If I include everything which I don't consider, of course, I have to write equals. I added here I remember, if I remember well, because a student asked me about that. Anyway, this expression here is the linear approximation of the function fx at the point x0. Now, our point x0, we can see here, is exactly our x hat k minus 1 in accordance with the definition, which I told you. Why that? Because this here was, or the is, this point here. This is the calculation of my system at x hat k minus 1, of course, and u k minus 1. Look, it's exactly what I told you. Is the function f of x0. In high school, you can consider this expression here complex, of course, f of x0, or let me say reflects f of x0. Basically, the function calculated at x0. What is x0 in our case? Again, I would like to calculate my field, my complex function, which depends of current, velocity, and u at x at the approximation at the step before. And of course, u calculated at the step before. This is the, let me say, our goal to approximate the function f at point x0, and I try to clarify what x0 is. Now, the rest, excluded this, is the derivative at point x0, which in our case becomes the Jacobian. Because as I told you, the Jacobian is an extension of the derivative when we have more than one variable. If you have more than one variable, of course, I have to consider the matrix and not a scalar. Calculate it again in our point x0, which is, in our case, is complicated because it's x hat k minus 1. And to be precise, I have to also consider u k minus 1 if this depends of u k minus 1. X minus x0 is exactly what we have here. X, in accordance with what Kalman is, minus x0, what we want to approximate. Then we have the noise, everything which I can consider as noise because these variables are stochastic variable. I do basically the same, we can see here, in terms of the output. Here is exactly h calculated at x0. I don't know if you remember. I probably is also here. Yeah. This set k hat minus, exactly this here. Yeah. In terms of output. Now, of course, we have to consider what is the new x0. No? It is one. For the output. In accordance with what I told you here. Okay, let me show you an example. Here you can find a comparison between, we can see here linear and nonlinear. But let me, and then here we have again the nonlinear as yeah, sum up everything. But the difference is just this approximation in terms of Jacobians. Considering the tuning, of course, the concept remain the same, but I would like to summarize everything saying that the convergence is not guaranteed anymore. And also the optimality. Why that? Because now we are, in this case, because the problem is not convex anymore. This means I could have more than one minimum. No one guarantees that I will get really the minimum. I have to start close to the minimum to have the probability that I'm going here, adjust the probability, but it's not guaranteed. And now you can consider also that it could happen that we have also no convergence. This means instability, because the problem could be the function to be optimized, the P to be optimized, the a posteriori error covariance, not necessarily is convex. This means it could happen that I don't have, let me say roughly that the Kalman filter doesn't work at all. But of course, if you are close to the global minimum, the probability that I will remain here and then I will converge here is high. In particular, if P0 we have seen is not so large, we pay this price within a slow convergence, but we remain here. Of course, if P is large, the Kalman filter can react very strongly, and then could happen that is in this case is not the linear case. We have the instability. Of course, starting from this region here, I will obtain a suboptimal solution. This means larger covariance, but the problem is we have a small bias because the estimation, the value is here. Or assuming that the value is here, we obtain this. This means, of course, it's not bad, but it could if this is the true value, with the minimal, say to the minimal variance, we have a difference between what we obtain and what we really we have. A few minutes, I will present the case, and next week I will do the simulation, repeating everything. Open the other presentation, which you can find in my study, very shortly to introduce the topic of next time. Next time we will see also the simulations. In the file of application, I think I already uploaded this because I think I introduced this. This is the example of the constant, the example of the of my model, which I reconsider today. Look now this. Very shortly to introduce, a few minutes. What I am doing here is I try, let me say, to introduce the variable R. I mean, I have a linear system. What I have seen today. The continuous system is this one. Two variables to be estimated, current and omega. We have seen today. We have the discretization, we have everything. Now, assuming that I would like to estimate also the parameter R. You can consider the parameter L. No, it doesn't matter. How many parameters we will see in the next lectures I can consider to be estimated together with current and omega. This is the state, the physical state must be estimated, but I can consider to estimate R because I need R, or I can consider to estimate L because I need L. I can consider to estimate both. How many parameters, because we can see we have also Km, how many parameters can I estimate? We will discuss together in the next lectures. But assuming that I would like to estimate R. This means if I would like to estimate R, I have to consider R as a state. We can see here. The derivative of R equals something. You remember the idea, if I don't have any hypothesis of R of t, is to consider the derivative of R equals 0. Is exactly what I'm doing now here. I mean, this minor here, these four elements are exactly the same which I considered before, but R is a function of time. Why that? because R now is in a state. We say augmented state because it's not exactly in a physical state. Admit originally R does not represent directly the energy. We are not interested at the beginning, at least in my didactical introduction, to estimate R. Now, if we are interested to estimate R, what we can do if I don't have any hypothesis of R, to introduce R as a stochastic variable. In particular, I can consider R as basically a Gaussian variable in which the derivative is zero. We can see here. The derivative of R with respect to t is 0 multiplied the current, yeah, plus 0 multiply omega, plus 0 multiply R of t, plus 0 multiply u input. No? We can see here, rho multiply column. We will see now next week how, if I introduce this model here, augmented model, I can estimate I, omega, and R as long as the system is observable, because I will generate an stochastization of the R. Do you remember we have seen this? We have seen just for the variable, but I can do the same consideration here. And I can estimate all states I, omega, the physical state, plus the augmented state. But what do we have here in this case? We have an extended Kalman filter because we have a nonlinear structure. Why a nonlinear structure? Because introducing the new variable R, we have R multiply current in the first line. Rho multiply column, we have R divided L, but R of t, which is in the new state, augmented state, multiply the current. This means we don't have a nonlinear case, but we have a nonlinear case, even though a little bit artificial, because we are considering augmented state. But the states are three: current, omega, and R of t. And I can consider the discretization of the model, which we have here, equation A, we will see next week more in detail. Very important. I can implement in MATLAB exactly as I told you. And this is the model nonlinear. We can see it's nonlinear, discretized, but nonlinear, because R multiply the current. R multiply the current. This is the discrete nonlinear system. Then building the, let me say, the Jacobian, calculated at the preview estimated x, and in particular, if I have an independence of u at the previous u, I will have my Jacobian, and then I am able to implement in MATLAB. We will see next week in MATLAB. In this case, the nonlinearity is an augmented nonlinearity, or the nonlinearity came from the augmentation. We don't have nonlinearity in the output. No? We don't have the nonlinearity on the output because the output is just what I am measuring as before, the current, for instance. Next week, I will repeat this a little bit, this theoretical part based on the application. And then we will discuss together the simulation. Okay, if you have question me. Otherwise, we will see next week. So next week, we will complete this nonlinear part with the simulation, and then we will go ahead with variations of the extended Kalman filter. Thank you for attending the classes. We will see next week.
Bye-bye.
Ciao, thank you.